Hello and welcome to another video of daily Leetcode challenges. Let's begin our question. All right, question 1345, jump game 4. Given an array of integers r, you're initially positioned at the first index of the array. In one step, you can jump from index I to index I plus 1, where I plus 1 is less than the length of the array, not going out of bounds. I minus 1, where I minus 1 is greater or equal to 0, so not jumping out of the left bound of the array. And j, where j is equal to the value, j is equal to index j, such that value at index I and index j are the same, and index I does not equal index j. Okay. Return the minimum number of steps to reach the last index of the array. Notice that you cannot jump outside of the array at any time. That's given to us by these instructions. Okay, example 1, r 100, negative 23, negative 23, 404, 100, 23, 23. Okay, so let's see. How's the output 3 from 100? Would you go here then? Oh, you would go to index 4. Then you would go to index 3. Oh, and then you would go to index. So, okay, so the value of the R array is sort of like the portal, and then the left and right steps, those are the more natural steps. Okay, this makes sense. This sounds like a snakes and ladders question. I'm gonna link it somewhere here. It sounds like something like that, where essentially we had to also reach the end of the array in the shortest amount of time, and we were able to skip either forward or backwards. Let's see if we can apply that logic here. What about this? This makes sense. We're starting at 0 and we're already at the end, so index is the last element. You don't need to jump. Example 3, we are 7, just one jump from the start to the end. Okay, if you watch my snakes and ladders video, then you would remember that we went about it the following way. We had a queue, which was just an array, and then okay, let's talk before we code. The premise of the problem is that there is a final destination that you're trying to reach and the least amount of steps. The condition by which we move is defined to us here, and the logic in the algorithm goes something along the lines of: we start at the 0th index, we look at all different neighbors being either the chute or the ladder or the snake in this, or a portal in this case, and then the two neighbors, we add them to the queue to be explored with the condition that when we're exploring those neighbors, we are incrementing the step that we are currently on. So initially we're at step 0 because we have not moved anywhere, but as we progressively add these elements to the queue to visit and to kind of look where we can travel from those places, we increment this notion of a step that actually tracks and tells us how many steps it took us to get there. So what we need to do, what we need is a, let's call it a distance array. Distance array that's going to be, let's say L is equal to length of R, because that's the maximum number of steps that you could take, and L is just going to be distance array. Sweet. Now that we have this, we are saying that our toVisit, which is our queue, is going to be implemented as an array. It has a 0 starting point, and what else do we need? We need to say that distance at 0 to travel to the 0th index is actually 0. So we say while toVisit, saying that while toVisit is not empty, we're going to say that current pause equals toVisit pop the first element. And now we implement our condition. We have 3 conditions by which we could visit or create neighbors. We can say that, let's see, left is equal to cur pause minus 1, right equals cur pause plus 1, and so we also actually need another data structure to keep track of these guys. The left and the right indices are given to us immediately, but what we don't know is which other indices we can jump to from our current index based on this value. So let's have another data structure here. It's going to be val t indx, val to index. Index, which is going to be a default dict of list, and let's populate this guy. So for I n in enumerate R, we're going to say that val to index at value n is append I. So for each value, be it 100 or 404 or -22, we're going to have a list of indices that we can go to. Sweet. So now we have these left, right, and the list of jumps. How would we call this? Jumps. This would be a list, and then the value, which is cur pause of R. Okay, sweet. So we have this, and now we can just check that if left is greater or equal to 0, and okay, so yeah, we can blindly visit left, but what we actually want to do is probably check, okay, I want to check another thing. So I'm going to actually take this away from here. No. Sorry. Give me a second. Distance. Steps. I'm going to have a steps variable indicating how many steps it first of all took me to get to the place where I am. That's just going to be distance cur pause. And now I'm going to say that if and steps plus 1 is less than distance of left. In that case, so this is the obvious condition. This is a bit more confusing, but what this is saying is our distance array, which holds the number of steps to get to a particular point, to a particular index, we will only be updating we will only be revisiting left if we can do so, if we can visit it in less steps than currently needed, or currently it takes to get to that index. Oh, wait, am I actually doing this? Right, yeah, I am. Steps. I'm going to say that dist of left is now equal to steps plus 1. And I'm going to say to visit append left. Okay, same logic for the right. If right is less than L and steps right, then I'm going to say that right is going to be steps and append right. And finally, for jump and jumps, which is just the array of places to go, I'm going to say that if, basically the same logic, if jump is greater or equal to 0 and jump is smaller than L and steps plus 1 is smaller than dist jump, then I'm going to say dist jump equals steps plus 1 and to visit append jump. And finally, we are just returning the last element. First try. Wow, sweet. However, time limit exceeded. So we are, okay, so one of the conditions is probably that the input array can be crazy large, which, yep, crazy large. Okay, so somewhere we have to optimize this logic. Okay, let's think. Currently, the way that we're adding things to explore is currently the indices that we're adding to the to visit data structure is actually, let's see if we're doing something redundant. If we are doing something more than we should. And this might be a good example. Let's see, 777. So after the first time that we're doing this, we are on the 7th element, so we add this guy and the 7th element somewhere here to our to visit array. Then we're adding this guy again here with the distance clearly not, the distance of this will clearly not be smaller because we've seen it previously on a smaller we've visited it on a previous account on a previous step, so visiting it on a later step would be completely pointless because it's the next step. We're not getting there any faster, we're getting there a step later. So okay, so how do we, okay, proposing my first improvement is we have a we don't revisit a node or an index that we have already visited. Why? Because as we are using our queue, and be sure that this is a queue, actually I should probably to visit, let's call this a queue here. To visit queue, there will be no point at which we revisit a node with less steps. Is that correct? Can we revisit another index in less steps than we have already visited it? No, we cannot. Let's have a visited set, and let's say visited add 0. Let's say that, okay, how do we visit this? Visiting. We visit when we pop. So visit add cur pause. Sweet. And now in all of our conditions, we're going to be saying and not visited left. And this is going to say and not visited right. Am I saying something wrong? Am I using this correctly? And left, not in, sorry, brain freeze. And right, not in, and here we have the jump, and jump not in visited. Okay, that's the first improvement. Still correct. Let's see if this decreases our time. Still time exceeded. Okay. Okay, honestly, there's another thing that I could probably do that has to do with this queue. So in Python, this is kind of abstracted away from us, but in reality, when you pop a 0th element from a list, you actually have to rewrite the whole list. So what I'm proposing is we actually use the DQ element, pop left, and this should theoretically increase our speed. Still time exceeded. So we're popping left. We're not revisiting. Okay, wait, did I write the visit correctly? Are we... Yeah, no. I'm fine. Should this be an array? Sorry, visited add set. No, this is fine. Okay, another thing that I was, sorry, where's our error that was with the sevens? I'm thinking that if we hit a value that has basically the whole index as part of its key value pair, so val to index 7 in this case has all of the indices. Once we add it, once we traverse it once, do we ever need to revisit 7 ever again? Can we just completely remove it from existence? Could we say that basically this, delete this guy forever? Okay. Okay, I'm gonna quickly explain what I did here. The problem was we have this val to index dictionary with key value pair value, key being the value, basically the value in the R input array, and the value, sorry, the key being the value in the R. Fine, I'm just going to speak by example. 7 and all of the indices as a list of And what I'm saying here is that in this while loop where we are looking through all of our potential jumps, potential small jumps, once we hit this guy the first time, once we hit that key value pair 7 and all of the indices and append it to our queue, we no longer have to look at it ever again, right? So although the value here will be reappearing, let's see, the jumps will be reappearing constantly because 7s are scattered throughout the whole array. We actually don't need to do that because we've already visited them once and we never need to do that again. Okay, so that's one thing. Let's see, what can we do more? I feel like 50 is good, and we're using a lot of time. Where else could we be using it? We're not looking at, let's clean this up a bit actually. I like jump right here. One thing that I'm thinking is I have this dist array of distances to a certain value, but what if I could, well, first of all, if cur pos is equal to L minus 1, return steps. Would this make me faster? Go any faster? Okay, a little bit better. So now I'm no longer iterating through the whole thing. Let's see if I can utilize another trick to maybe speed this thing up. Obviously, let's put some conditions here that if, where's my L? I like defining the values that are used the most first. If L is smaller or equal to, is there a smaller or equal to? What is the length of, if L is equal to 1, return 0. And there's one more thing that I wanted to suggest. We have this distance array, right? But in reality, we could sort of keep track of which nodes return or which nodes, which indices require how many steps with a single value. And that is going to be steps. So look at how you can basically remove the need for that whole array. We have this steps value that keeps track of the, think of it as like a breadth first search, right? You have a steps value, and as you're adding elements to our queue, we know that the next level of values to visit are only going to require one more step. And so what we're actually going to do now is, instead of just blindly revisiting or popping off the next node from queue, we're going to say that for in range len to visit queue. What this is going to make us actually do is on the first iteration, we're only going to have one node in there. That node is going to be the only value. This does seem redundant, but what we're doing here is, for one node, we're looking at all of its children, and then the next time that we're hitting this whole thing over again, we're actually just in this for loop, we're iterating through the next level of the breadth first search tree. And now we just increase steps, because that's when we exit to the next level of the tree, and we remove completely this. We don't need this anymore. We don't need this. And do we actually need this then at all? Or do we just, let's see. We might not need this anymore because why? Because of the previous statement that if we already visited a node, so this visited set, if we already visited a node, it's guaranteed that we visited it in less steps than what we're going to be visiting it in again. So this condition here and here and here actually is taking care of the previous condition that I just deleted that said that let's make sure that the number of steps to get there is also smaller than the current number of steps, because it's guaranteed that if we visited it before, it was in a higher tree level, meaning that the number of steps to get there was less. Let's see if this counts. And okay, so somehow we have decreased the number of somehow we have made it slower, which does not make sense to me. How could that even be? How could that be possible? Let me just submit it again. There are times where no, it's consistently saying that we're messing something up. Okay, let me just try one thing quickly and make sure that Okay, what I did there was yeah, it yeah, I kind of just I added the nodes that we're visiting a little bit earlier than when we've already hit it, just to make sure that if it within the queue there already exists a node that we visited, then we can mark it earlier on. And I mean, this is already pretty good. Let's see if there's some more clever solutions maybe that we can utilize. DQ. DQ. It's very similar to what we have. Pop left. Okay, interesting. So here they're suggesting to do the jumps first rather than the left and the right. What that could be doing for us is since the jumps are there's more chances for a jump to be how do I say this, reach out into the far and potentially get us closer to the ending value. It could be that we would be hitting it. This would be speeding us there up a little bit. In terms of things like this could be annoying. DQ, step, all of these things are visit. Looks almost at this point it looks almost one to one, and it slowed us down even more. Yeah. Okay. 72, good enough. To be honest, the chances of this being a there we go. Okay, so I'm convinced that the little fluctuations in time, they're just with the they're just because the question has some very big values, so it tends to be sometimes it's just by chance that you get a runtime that's lower than the previous. So okay, here's the solution. Let me make this a little bit cleaner. Not cleaner, but more compact. Is this even allowed? Just because I want to fit it all into one. Let's see. Gives us a better runtime. No, not a better runtime, but at least you could see the solution in one take. I'm still linking the video to the snakes and ladders first because we kind of build off of that. But the idea is very simple. We have a breadth first search where the level of the tree indicates which step we're on, and we are essentially just populating that that tree with next potential jumps, making sure that we don't revisit a node that we've already been to, And yeah, and the condition here is pretty straightforward. You can either jump to a index whose value is the same as yours, your value at your index, or to the left or to the right one. So yeah, a BFS question, basically. A little different than the snakes and chutes and ladders question. But thanks for watching, and we'll see you later. Bye.